Pi can be written in binary, so the universe can be represented in a sequence of ones and zeros. However, pi is just one transcendental number, and there are an infinity of them. Each sequence would have a unique mapping to our universe. Similarly, the values could map to a possible world, a different world. All we need to do to represent it is a change in the mapping. Hey Sapiens, and we're back. So last time we were talking about a lot of cool stuff, ethics, AI, but also computer science as fundamental. And we're going to continue talking about computer science and see how far the idea of computation and programs extends. But I also want to talk about a related concept real quick, which is chaos and reductionism. So someone who explained this really well is Robert Sapolsky. He's actually a Stanford biologist and has a super popular lecture on ethnology, which is animal behavior. And YouTube bombarded me with his videos and kept recommending them, and then over and over and over until finally I just gave in and I said, all right, YouTube, what do you want to show me? And then I got hooked and I watched 26 episodes of this guy's lectures on animal behavior, but one of them was about chaos and reductionism, which is super interesting. He drew upon the work of Chaos Making a New Science by James Gleick. There are systems which have periodicity. So like a clock has periodicity. We can expect at 9 a.m. that in 12 hours, a clock will return to 9 p.m. We try to compress the phenomenon down to an equation or scientific theory to explain or predict the system. We can describe a line in a graph with the equation y equals mx plus b. So reductionism attempts to understand systems at lower levels than the whole to reduce variability and noise. Perhaps if we understand all the small parts, we can fully predict the whole, like reducing an organism to its genetic code. However, genes are actually an example against reductionism. There are billions of connections in the brain, but there aren't billions of genes coding for each connection. The code gives rules for a pattern, but the pattern can be perturbed by initial conditions. So each time you run the code and generate the pattern, it will turn out differently. We attempt to reduce variability and noise to find that both are features of the system which are scale-free. So it doesn't matter how big or how small you go. No matter how much we reduce and magnify, no matter how far we zoom out to study the whole, there will always be variability, noise, and mysteries remaining. Like the value of pi, the more resolution of the number we hope to have by finding a new decimal place, we can determine the next digit giving greater precision, but the value doesn't end. We can zoom in for precision endlessly. One cool example is thinking about Mandelbrot sets. Imagine a person who just wants to understand one small part of the Mandelbrot set, just a piece. You can magnify a small space, attempting to see the smallest magnification levels, but Mandelbrot set is defined based on the magnification level you look. We exist on a plane in a size that determines our magnification and level. We can gain local information, but we hit limitations by magnifying. So I think this is like the search for the meaning of life and understanding the universe. There is always more to learn. We can magnify ourselves. We can look at people on the whole person level, or we can magnify down to the smallest unit of us, a single cell. At the cellular level, we see a different yet familiar world. Cells interact with their environment, reacting to stimulus. Cells are able to self-replicate by dividing. Cells process information about themselves and their surroundings in variables of size, location, age, and time of day. Cells have some form of memory, at least genetically, about how to handle different circumstances. Cells self-regulate. Cells go against entropy, exchanging outside energy to maintain internal order. By performing these actions, cells trap and create more information than their surroundings, as we saw in Why Information Grows. Cells have a code, a program, given in the RNA and DNA of the nucleus and separately in mitochondria. DNA has symbols and a grammar. There are codes which signal when to stop reading a genetic snippet of information. DNA has jump statements, branching, control flow, essentially like an if statement in programming. But another amazing person, Joscha Bach, wow, he's incredible. As Joscha Bach puts it, cells are self-replicating Turing machines which exploit entropy gradients created by the laws of physics. So by existing, we shed bits of information, which amounts to information processing. Gosh, Joscha Bach, he also talks really fast, and you have to unpack everything he's saying very slowly. But we're going to talk about Turing machines now. So I mentioned it before, getting back to it. And the idea of Turing machines, though, is what is a computer? What is computation? This is actually a really difficult, complicated question, but Alan Turing set out to formalize these concepts. Computation is the systematic flipping of bits. A problem is computable if you can reduce it to mechanical symbol manipulation. Our universe can be seen as a computer in that the change we see is the change of information. The program the universe follows is according to the laws of nature. So there are a lot of cool examples of Turing machines, but computers are a controlled energy flow. They process and recombine information. Built from the logic gates up, computers are reasoning made tangible. Binary is represented as 0 and 1, but can also mean on, off, true, false, up, down. In school, you might raise your hand to signal you have a question. Notice that we can change the context to change the meaning of raising your arm. With one arm, we can represent 2 states. With 2 arms, we can represent 4 states, flipping all over. Here's an interesting if with this binary counter, and you can see how to represent numbers greater than 1 using binary. The bottom light orange numbers are only 0 and 1, the binary. To the right of it, on the right-hand side here, you see that the number is in base 10 and the type of counting you're used to. So we normally think of it as base 10. And you can find the number in base 10 by adding up the values in the middle column wherever there is a 1 beneath it. The top row shows the powers of 2. So there's a lot of great resources on learning binary and, just to get a sense of it. But let's think about base 10. So in base 10, 952, as an example, is really 9 times 100 plus 5 times 10 plus 2. We can write the same thing as powers of 10. And we could say it like, 9 times 10 to the second plus 5 times 10 to the first plus 2 times 10 to the 0, which is 2 times 1. Because 10 to the 0 is 1, any number to the power of 0 is also equal to 1. So from the rightmost digit, we see a pattern where each number is 10 to the power of the digits starting from the right at 0. So binary is pretty much the same as that, the same as base 10 of what we're used to. But in binary, we change the base to 2. So instead of 10 to the power of whatever, it's 2 to the power from digits from the right starting at 0. 101 in binary represents 1 times 2 to the 0 power plus 0 times 2 to the 1 plus 1 times 2 to the 2, blah, 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 blah. It's 1 plus 0 plus 4, which is equal to 5. So in binary, 1, 0, 1 is equal to 5. And basically, just like in base 10, in base 2, we can do addition. And from here, we start to build up to some of the more complex arithmetic operations. But anything written in base 10 can be rewritten in binary. Most systems like your computer expect a certain length of binary digits. The term binary digit was compressed to the word bit. A byte is 8 binary numbers, bits, in sequence. Negative numbers can be represented by making the first bit 1. So 4 and negative 4 would be these long sequences. But notice that this changes the range of numbers we can express, since the leftmost bit would be 1 times 2 to the 7th, but is now a question of sign, plus or minus. We can also use binary to represent letters. Instead of 0100 mapping to 4, we can say 0100 maps to the 4th letter, D. In a similar way, we can represent anything written or spoken in terms of an alphabet translated to binary. So again, it's just we can make binary represent letters in the alphabet. But think about this. If we map one binary string of bits to one number, letter, or other idea, how many items can we represent? The ability to map is equal to the number of distinct binary sequences that can be made from a given number of binary digits, like a byte of 8 bits. Binary represents one of two options, so there are two ways to choose. At 2 bits, there are 2 ways to choose the first digit and 2 ways to choose the second bit, so 2 times 2 is 4 sequences, 4 possible mappings, and so on for n given bits. But we can map 2 to the n binary sequences. With just 32-bit sequences, we can have encoding for, 4,294,967,296 things. Using simple binary, we can represent more complex concepts. All we need is a system that understands what each bit's 1 or 0 represents, an answer to a question. For a computation, the question is based on the rules of how the information is processed. How does the information grow from binary? Binary addition, as an example, gives us a new output sequence from 2 given binary strings added together. New information generated from given information. As expressively powerful as Turing machines are, they are of course limited. They function on deterministic processes, and there are problems which cannot be computed, like the well-known halting problem. Other than giving us computers, these ideas have spawned entire fields of theory. One such idea is algorithmic information theory. We can differentiate Turing machines based on the rules they follow to flip their sequence of bits. The rules are the program. This allows us to define Occam's razor in terms of programs. Occam's razor was originally used by scientists to determine which hypothesis to use in explaining observations. We can reframe this in terms of the minimum description length. So this is really cool, where the description length of a data sequence is the length of the smallest program that outputs that data set. A program can be a hypothesis. It's how we think the data might be generated. The measure of the smallest program to produce an object, like a string of letters, is Kolmogorov complexity. Okay, so I hope this is clear. I'm going to try to re-say this again, but it's really interesting. Basically, from binary and bit flipping, we can get to computer programs, and we can describe science in a way of programs. So a hypothesis is like a program that allows you to generate a sequence of bits which maps onto data that you would see in the real world. And basically, the simplest program that you could use to generate the data that you observe, that is the minimum hypothesis, the simplest hypothesis that you can have. And so this spawned a whole interesting theory about algorithmic information theory, but Kolmogorov complexity, which is, just how can we find that proof of the smallest program to find what would generate that sequence of bits. But I say this because it's also related to Solomonoff's theory of inductive inference. There are multiple competing programs or models that fit the data. When a new observation is not predicted by the model is falsified. We have the remaining programs to choose from, which we give the highest weighting to the simplest. So basically choosing the most minimal hypothesis program. So there were, and I guess there are still a lot of problems with inference, but with Solomonoff's theory of inductive inference, we really were able to, in a lot more of a systematic way, talk about inference, inductive inference, going from specific to the general. And this goes back to critical rationalism as well, when we talked about, falsifying models. And in a way, I hope this makes more sense too when we talked about you don't want to corroborate your model so much. Like if your model makes an accurate prediction, well, it also has competing models, most likely, which also gave that same accurate prediction. So they are all supported. But the real information is when a model is falsified, when it makes an incorrect prediction, because then you can cut it off, versus when all of them are making correct predictions, then you don't cut any of them off. So again, you want to look for that criticism, that falsifying. Earlier in my life, I focused on the storage of information. To have experience and reflect on it was a good in its own sake. To store information persists its existence and meaning. As I learned more math, I realized the data for a complete mapping of the universe exists infinity times over. Consider the value of pi. So this was like a meme that was floating around, but it's really interesting to think about. Pi is an infinite, non-repeating decimal, meaning that every possible number combination exists somewhere in pi. Converted into ASCII2 text, binary, somewhere in that infinite string of digits is the name of every person you will ever love, the date, time, and manner of your death, and the answers to all the great questions of the universe. Converted into a bitmap, somewhere in that infinite string of digits is a pixel-perfect representation of the first thing you saw on this earth, the last thing you will see before your life leaves you, and all the moments, momentous and mundane, that will occur between those 2 points. All information that has ever existed or will ever exist, the DNA of every being in the universe. Everything, all contained in the ratio of a circumference and a diameter. Wow. So there could be a potential mapping of the digits of pi with meaning to our universe. Finding that mapping would be incredibly difficult, but possible in principle. To represent our universe, we would likely want a more ordered value series than pi. Notice the digits of pi, which are represented in base 10, can be represented in base 2. Pi can be written in binary, so the universe can be represented in a sequence of ones and zeros. However, pi is just one transcendental number, and there are an infinity of them. Each sequence would have a unique mapping to our universe. Similarly, the values could map to a possible world, a different world. All we need to do to represent it is a change in the mapping. Using Leibniz formula to calculate pi, we can write a very short program to output the value of pi. So the Kolmogorov complexity of pi is actually quite small. However, the Kolmogorov complexity of the program which maps the values of pi in a meaningful way to our universe would have extremely high complexity. So I hope that makes some sense. In some ways, even though something is non-repeating, endless, infinite, and variable, we can write a really small program to calculate that. But when things become more complex, then your program has to be even bigger and bigger and bigger, and the complexity of that grows drastically. So pi can be calculated in a few lines of code, but to map pi in a meaningful way to our universe would be a ridiculously large program. Okay, so that was a long preamble, and you don't have to understand everything. I apologize for all that. You can dig into the links deeper and think more about computers, but I also put this as more of a foundation so that we can talk again about the Ladder of Causation from the Book of Why, and we talked about cause and effect. So the Ladder of Causation in terms of logical statements, and this was just something that I thought about, that this is like a big insight for me personally. We talked about the association level, the intervention level, and the counterfactual. So that was seeing, doing, imagining. The association level is simply ands, an and logical statement. So we have x sub 0 and x sub 1 and x ... sub n. So the association level is just these and statements, anding information together. The interactive level is gaining control over the bit flipping in the form of an if statement. So what if x sub 0, then y sub 0? Imagination is a complicated chain of the second level. So if we said what if x sub 0 and x sub 1 and yada yada yada, then y sub 0 and y sub 1 and y sub n. Imagination also allows for counterfactual reasoning, why we would not have an expected outcome. By chaining together a series of possibilities represented as flipped bits and using our causal model to estimate the outcomes, we gain counterfactual reasoning of simulated worlds. We can imagine possible worlds and make inferences from them. So, some examples of this. So what if people were twice as tall? What would be different about that world? We're changing something simple about a feature of our world. So if you think about, you take everyone's height and double it. So whatever your height is, double it. It's a quick flip. Would doors still be the same size? And a child can answer that. No, they would be twice as big for people to get through. We understand doors are made by people and the size is related to average height. If average human height changes, the average door size changes. But again, this is just talking about how we can start to understand cause and effect in terms of programs and logical statements and flipped bits. But we can talk about sending and receiving information and entropy, bringing entropy back into it. Taking a look at information again, a good definition of information is the difference that makes a difference. For two pieces of data, how can you tell them apart? In binary, we have the clearest difference, 1 or 0, yes or no. What if we frame a bit with context? What if each bit is asking a yes or no question? Imagine we're sending messages to each other through a computer, but one person doesn't have a microphone. That person has to communicate yes or no visually. Given the English alphabet A to Z, how many yes or no questions are required to spell the word one? Well, let's start with the first letter O. What question would you ask? Since there are 26 letters in the alphabet, you might think we need to ask a question for every letter up to O. Is it A? No. Is it B? No. Is it O? Yes. What is the fastest way to determine the correct answer, the correct letter out of all the possible letters? Well, let's start with a smaller list of possible letters, just to simplify this problem. Say we want to send one letter from A through E, so that's 5 choices. We can ask, is the letter after C? If yes, we know the letter is D or E. Let's say the letter is E, just as an example. Then we can ask if the letter is before E. No. The letter is E. So if no, then the letter must be D. We're starting to really cut down on that. If the answer is no to the question of is the letter after C, our new shortened list is ABC. We can repeat the process, asking if the middle letter is before the letter meant. So is the letter before B? No. So the only letter after B is C, our answer. By asking this yes or no question about the middle letter, we can quickly dismiss half of the answers. If we know the intended letter is on one half of either side of the letter, we don't have to bother with the other half. Each time we ask a question, we divide up the possible answers into 2 groups. Mathematically, dividing up input repeatedly is a logarithmic, so log base 2 operation, which makes it much, much faster. A part of all this is to explain that how information is stored, shared, and processed has calculable limitations. We can send information very efficiently and accurately, or inefficiently with many errors. There are boundaries on how fast we can send a piece of information, which is to say how fast a receiver can remove uncertainty. An alternative explanation of entropy from a more human perspective is that entropy can be a measure of uncertainty. We can define entropy as the minimum number of yes or no questions we need to ask to remove uncertainty from the system. Entropy is the minimum number of questions needed to have full information. So here's another example that might take a little bit of thinking, but imagine a box full of 400 H2O molecules. When the H2O is in the state of an ice block, the structure is rigid. How many questions do we need to ask to specify where the H2O molecules are in the box? What about when the box is liquid, just a pool of water at the bottom of the box? The H2O molecules spread out, they're looser. Their position in space of the box is less rigid, more variable. So we have to ask even more questions than when it's a solid. When the H2O is gas, where are the molecules? Now they can be just about anywhere in the box. We have an intuitive sense, a model of how the material world works, that the ice and water would be at the bottom of the box while the gas floats. We can divide up the points of space in a 3-dimensional box as the yes or no questions of, is an H2O molecule here? In ice form, we should be able to find the molecules quite fast. In liquid, less fast, but gas would take the longest of all. If we track a specific molecule, the rise in uncertainty as to where the molecule is as the H2O molecules change in state from ice to water to vapor is the nature of entropy. Basically, the more energy something has, the more uncertainty about its position it is, increasing its entropy. Okay, so we talked a lot about information and sending and receiving information, but bringing this back to life, we can think of ourselves as an evolutionary algorithm. And some people, like Yuval Noah Harari, have labeled us living people, organisms, as biochemical algorithms. Biochemical algorithms are a lot of how we actually function day to day. But we can, again, formalize an evolutionary algorithm And essentially there's two steps, which is step one is generate the initial population of individuals randomly. So that's the first generation. Step two is to repeat the following regenerational steps until termination. So these four steps are: one, evaluate the fitness of each individual in the population. We think about time limit, sufficient fitness achieved, etc. Step two there is select the fittest individuals for reproduction, which are parents. Three is breed new individuals through crossover and mutation operations to give birth to offspring. And four is replace the least fit individuals of the population with new individuals. And this is an evolutionary algorithm which can actually be used to solve problems. And it's a little weird, but you can see evolution taking place in a computer. But here we're speaking of fitness in the context of evolution. And this is a quote here from Fitness in Terms of Biology. The term Darwinian fitness can be used to make clear the distinction with physical fitness. Fitness does not include a measure of survival or lifespan. Herbert Spencer's well-known phrase, survival of the fittest, should be interpreted as survival of the form, phenotypic or genotypic, that will leave the most copies of itself in successive generations. So again, fitness is really about survival. It's about finding your niche, about finding your energy source that has lower competition or that you're better at. But now we get on to something that's really interesting. And it's a paper called The Fitness Beats Truth in the Evolution of Perception. The authors present and prove the fitness beats truth theorem through evolutionary game theory and Bayesian decision theory. Evolutionary creatures who favor seeing the world truthfully and objectively will fail in comparison to creatures who see the world to maximize fitness. A quote from the paper here: our main message in this paper has been that contrary to this prevalent view that we perceive objective reality accurately, attempting to estimate the true state of the world corresponding to a given sensory state confers no evolutionary benefit whatsoever. Rather, a strategy that simply seeks to maximize expected fitness payoff with no attempt to estimate the true world state does consistently better in the precise sense articulated in the statement of the fitness beats truth theorem. So, I mean, you can look at that paper to see exactly what they're saying, but it does have pretty wide-reaching effects. I mean, that's interesting that seeing the true state of reality has no objective evolutionary benefit. Another quote here: evolution can fashion perceptual systems that are, in this sense, ignorant of the objective world because natural selection depends only on fitness and not on seeing the truth. As human observers, we are prone to imputing the structure to the objective reality that is properly part of our own perceptual experience. For example, our perceived world is three-dimensional and populated with objects of various shapes, colors, and motions, and so we tend to conclude that the objective world is as well. But if, as the fitness beats truth theorem shows, evolutionary pressures do not push perception in the direction of being increasingly reflective of objective reality, then such imputations have no logical basis whatsoever. So this does not bode well for us if we want to actually get in touch with objective reality, but it shows the odds we're up against. And this was quite devastating for me, but I was trying to think about it and to think of an example of how fitness would beat out truth. And so if you imagine two birds which both have the same diet of blueberries, one of the birds sees the full color spectrum as it is. In the rainforest, everywhere you look pops with vibrant colors beyond the capacity to name, so it's like technicolor. The other bird does not see color, but only black and white, while it does see one color, blue. The landscape this bird sees is a continuum of black, gray, and white. However, any blue object shines throughout the background of gray. The blue-seeing bird can spot anything blue with just a look. Now, which bird will be better at finding blueberries? Which bird will find them faster? And I think it's pretty clear that the bird who only sees blue will notice blueberries immediately, while the full color spectrum bird must sift and separate the light pollution of all the other colors. This is part of why bees see ultraviolet light and humans don't. If we saw the ultraviolet light, it would likely have little use in our daily lives. So someone else that I want to talk about is Donald Hoffman, and I'll mention him later, but I wrote this work before I read his book, The Case Against Reality, and he is largely working off this fitness beats truth theorem as well, and heavily leans into it in a way that even I think is extreme. But he sees consciousness as even more fundamental and thinks that we are so incredibly mistaken about the objective world. Like, we think that the world is three-dimensional, at least, right? That there's shapes and sizes and all these types of things. But a lot of these theorems say your epistemology, your ontology of what you think the world is like is just so wildly off. Like, you're so off you can't comprehend. And it could be so vastly different from what we expect. And another way to think about this is journalism versus genetics research. So in journalism, we're having a divergence from reality in a sense because they're trying to maximize payoff. They're trying to maximize the number of clicks they get, the number of ads that they show. And so they're exploiting parts of human nature, like things that outrage us or things that make us feel good or gossip or all this stuff. In the sense that it doesn't even matter if it's true anymore, it just matters if it gets a quick click. Whereas genetics research seems to advance according to the actual state or closer to the state of reality, because the more accurate you can be with genetics, the better payoff you get. And that seems to be a big trade-off here, that you have to match your payoff closely to the actual state of reality if you want to get close to it. Because you can seemingly totally separate your objective reality, the truth, from maximizing payoffs. And you can get some really wild ideas. This is again, though, why I think AI can be so incredibly important and why we can have an artificially intelligent creature who's much better at seeing reality as it is in a way that we seem hopeless, but maybe they have a chance. They don't have to be designed according to maximizing fitness payoffs. And they might be the first creatures who are able to bypass fitness payoffs and go for maximizing viewing objective reality. And I think it's even more reason why we should be investing resources to get them closer to objective reality. I mean, the best tools that we have seem to be like science and math, and that's still really hard for us to do. Additionally, what we see with fitness beats truth theorem is that fictions, human fictions, tend to be better for survival. And we're seeing that there's a lot of fictional things. So I hope I don't upset people too much, although I do enjoy doing that, but we're going to talk about religion. And I think it's important for the meaning of life because a lot of people do things in terms of meaning based on religion and God, and that forms a foundation. So in the belief of God, there is a question which will determine if you can hear the truth. I think this will separate people. Do you want to believe or do you want to know? Do you want to believe in God or do you want to know God? And that, I think, will really separate people. Where if you want to believe and you can just feel that, nothing's going to convince you. You're pretty set. But if you want to know God, I think you have a chance of seeing that it's more of a fitness-based thing than it is about reality. So if you want to believe, you're trying to hold on to the belief in God because it is comforting. If you want to know, then you will need answers, rationality, coherence. That is the path to understanding. While this applies to religion and belief in God generally, I will consider Christianity. The Bible reportedly lists commandments from God. The Bible tells us how to poop. We should have a spot outside of our encampment and bury our poop with a tool. So this is Deuteronomy 23:12-15. You shall have a place outside the camp and you shall go out to it. And you shall have a trowel with your tools. And when you sit down outside, you shall dig a hole with it and turn back and cover up your excrement. And then these are just some examples. So here's some scriptures that relate to eating and handling shrimp. Leviticus, these you may eat, and of all that are in the waters, everything in the waters that has fins and scales, whether in the seas or in the rivers, you may eat. But anything in the seas or the rivers that has not fins and scales of the swarming creatures in the waters, and of the living creatures that are in the waters, is detestable to you. You shall regard them as detestable. You shall not eat any of their flesh, and you shall detest their carcasses. Everything in the waters that has not fins and scales is detestable to you. Again, in Deuteronomy, of all that are in the waters you may eat these, whatever has fins and scales you may eat. So, as for homosexual activity, the Bible has two main scriptures. You shall not lie with a male as with a woman. It is an abomination. If a man lies with a male as with a woman, both of them have committed an abomination. They shall surely be put to death. Their blood is upon them. So, from a purely objective standpoint, let's think of the evolutionary benefits of each of these commandments. Bury your poop with a dedicated tool keeps humans from contaminating each other. If we don't have waste management, many of us will get sick and die. But by burying our poop, we solve many of these issues. And it doesn't take a lot of complex understanding, you just follow the rules. So why did God say to only eat fish with fins? In biblical times, thousands of years ago, shrimp were genuinely unclean. They gave you food poisoning. We didn't know how to clean them properly to reliably avoid getting sick. By avoiding them as a food source, many people lived. The Bible condemns homosexuality for both sexes, but is there an evolutionary benefit? The finer points are complex, but my guess is accepted homosexuality reduces childbirth for the group. In biblical times, your success and power were largely determined by the size of your group. Homosexual families have less children, so homosexuality is outlawed, increasing the number of sexually reproductive families. We can see at the time, all the scriptures contained a useful strategy for survival, which we understand more scientifically now. Groups of people who bury their poop will have less sickness and disease than those who don't. We don't care about burying poop now because the real problem is sanitation. Eating shrimp would have killed you in those days, but now we can properly clean them for consumption. Accepted homosexuality likely disrupted expected family planning. We don't need to outbreed neighboring competitive groups. However, we still deal with anti-homosexuality today. The support for behavior doesn't need to be well justified to get the benefits of the practice. A person who believes in washing their hands of any poop after they touch it get the functional benefits whether they believe the reason is due to germ theory or God says poop is a spiritual abomination. From the perspective of the fitness beats truth theorem and an understanding of evolution, we can see how the idea of God arises. The idea of God is a fiction which evolved into our minds. God has been with us in as many forms as our environment takes. When we are close with a thriving nature, sapiens believe in many gods and spirits. Hunter and gatherer tribes think that the gods are forces behind everything, but care little for human lives. They wouldn't have prayed to them. Sapiens which traveled in the desert began to believe in one God, the supreme God of survival. As we formed cities, the faraway universal God became a more personal God, which cares deeply for all of our personal woes. In cities, our lives depend on other humans. It makes sense that our God would listen to our prayers and understand us. The idea of God became a powerful force for attracting fictional beliefs and practices with real survival benefits. To this day, a Christian person can move to a new country and still have a community of support from a church in their network. Religious people continue breeding at higher rates and due to the structure of their religious community have more stability. If we look at religion as a belief system which can be viewed as a dissipative structure, we see religion is like a living creature like all ideas. If a religion doesn't survive in the minds and actions of believers, it ceases to be. For a religion to persist through time, it needs to be adopted, solidified, translated, and spread. Religions which change too much don't persist and are absorbed by dominating religions. The most popular religions are the religions which focus on converting non-believers into believers. Thus, they grow their numbers, winning at the group size game. Religion has constraints based on survival as well. A major downside to belief in God is what is called metaphysical baggage. So religion really sounds like something that doesn't exist or make sense. It's not much about cause and effect. We have to accept all of these ideas which don't match reality, like souls, afterlives, creation, etc. You might hold on to the belief that the earth was formed only 5,000 years ago, when all evidence and argument says much longer. Wouldn't this be bad from a fitness perspective? The truth of these claims don't have much of an impact on our day-to-day life. People can survive believing all kinds of falsehoods. In fact, declaring an absurdity, Jesus and God are one and the same, a part of a Holy Trinity, serves a group function. When people say extreme statements, they signal their conformity to the group. They're demonstrating loyalty by denying reality and mark themselves as a true believer. People have long known that religions give benefits and they follow the rituals without deeply believing. Some humans may be trapped into believing in some kind of a god. For generations, we have bred based on the religious teachings, intersubjective beliefs. Perhaps that has changed how some of us are structured. Perhaps God and religion are necessary parts of any intelligent species' evolutionary story, a strategy which boosts the whole species. We do have much to owe religion in its gifts to humanities, but religion served its purpose when our species could not bear the weight of our ignorance. So many of us cannot sit with uncertainty. Life is terrifying, full of suffering, and if we've lived long enough, we will feel empty of meaning. In God, we take all of the fear and uncertainty and ease it with answers or attempts to control outcomes with prayer and ritual. God represents a safety net, and the world is based on justice. People don't often pray for daily tasks, but more people pray and perform rituals in chaotic times with risky odds. Religion also codifies morality and passes on preferences. By describing pure and impure, religion shapes our sense of disgust. Religion builds buttons and reactions in us, then presses them for control throughout our lives. People in power have used religious people as a tool, steering them by hijacking authority figures. I think we should see religion for what it is. Once one of the best outlooks to get a person successfully through life, that is now obsolete. We should continue religion for what is good in it and abandon the rest to the Dark Ages. So that's just my take on it too, but I do think that having the idea of a God helps us to attach a lot of fictional beliefs in a unified way. It's also a really good story because people seem to generally accept and believe it, so it spreads. And I think there are also some other interesting psychological principles that this is preying on, like maybe it's an emotional memory from how we used to view our parents. Our parents seemed like a god to us when we were infants, and that memory stuck around so that we seem like we have so much faith that there's definitely a god. But that's getting a little further. What I want to say though is, moving on and continuing with the fitness beats truth theorem, we would expect to see brains with more internal input than external input. So that is, incoming sensory input matters less than how our brains transform the incoming data into a useful representation to maximize utility. And that is exactly what we see. So the input that you get is less important than the processing that you do to make that useful. So a really incredible cognitive researcher is Anil Seth, and he has a ton of great TED Talks, and I would recommend queuing some of those up. Those are really impressive, and it had a big impact on me. So he talks about how your brain hallucinates your conscious reality. One example of how the brain amplifies its own perceptual predictions instead of analyzing the raw incoming sensory data is the checker shadow illusion, which I'll pop on screen now. And again, it's really hard to believe this, but check it out. Do you see those checkers that say A and B? The image depicts a checkerboard with light and dark squares, partly shadowed by another object. The optical illusion is that the area labeled A appears to be a darker color than the area labeled B. However, within the context of the two-dimensional image, they are of identical brightness, i.e., they would be printed with identical mixtures of ink or displayed on a screen with pixels of identical color. And here's a second image, and you can see when they're connected, A and B, it's far more obvious for our brain that they're the same color. Even with the second image and various ways to verify the color of the two tiles, it is still hard to believe that they are the same color. Our brains sense the shadow and adjust the visual sensory input to convince our conscious mind that the colors are different. This applies to all conscious experience shaped by evolution. So again, he has a great talk, and I'm going to end this video with a long, good quote by him. Instead of perception depending largely on signals coming into the brain from the outside world, it depends as much, if not more, on perceptual predictions flowing in the opposite direction. We don't just passively perceive the world, we actively generate it. The world we experience comes as much, if not more, from the inside out as from the outside in. There's one last thing I want to draw your attention to, which is that experience of the body from the inside are very different from experiences of the world around us. When I look around me, the world seems full of objects, tables, chairs, rubber hands, people, you lot, even my own body in the world. I can perceive it as an object from the outside, but my experiences of the body from within, they're not like that at all. I don't perceive my kidneys here, my liver here, my spleen. I don't know where my spleen is, but it's somewhere. I don't perceive my insides as objects. In fact, I don't experience them much at all unless they go wrong. And this is important, I think. Perception of the internal state of the body isn't about figuring out what's there, it's about control and regulation, keeping the physiological variables within the tight bounds that are compatible with survival. When the brain uses predictions to figure out what's there, we perceive objects as the causes of sensations. When the brain uses predictions to control and regulate things, we experience how well or how badly that control is going. So our most basic experiences of being a self, of being an embodied organism, are deeply grounded in the biological mechanisms that keep us alive. And when we follow this idea all the way through, we can start to see that all of our conscious experiences, since they all depend on the same mechanisms of predictive perception, all stem from this basic drive to stay alive. We experience the world and ourselves with, through, and because of our living bodies. He says, let me bring this together step by step. What we consciously see depends on the brain's best guess of what's out there. Our experienced world comes from the inside out, not just the outside in. The rubber hand illusion shows that this applies to our experiences of what is and what is not our body, and these self-related predictions depend critically on sensory signals coming from deep inside the body. And finally, experiences of being an embodied self are more about control and regulation than figuring out what's there. So our experiences of the world around us and ourselves within it, well, they're kinds of controlled hallucinations that have been shaped over millions of years of evolution to keep us alive in worlds full of danger and opportunity. We predict ourselves into existence. Now I leave you with 3 implications of all this. First, just as we can misperceive the world, we can misperceive ourselves when the mechanisms of prediction go wrong. Understanding this opens many new opportunities in psychiatry and neurology because we can finally get at the mechanisms rather than just treating the symptoms in conditions like depression and schizophrenia. Second, what it means to be me cannot be reduced or uploaded to a software program running on a robot, however smart or sophisticated. We are biological, flesh and blood animals whose conscious experiences are shaped at all levels by the biological mechanisms that keep us alive. Just making computers smarter is not going to make them sentient. Finally, our own individual inner universe, our way of being conscious, is just one possible way of being conscious. And even human consciousness generally, it's just a tiny region in a vast space of possible consciousnesses. Our individual self and worlds are unique to each of us, but they're all grounded in biological mechanisms shared with many other living creatures. Wow. Well, thanks. Until next episode.